If the universe truly had a beginning, where exactly did the Big Bang take place? You might imagine a massive explosion detonating from a single hot center in space, sending galaxies flying outward like shrapnel. But the reality is far different. Thanks to modern observations and deep space mapping, we now understand why the universe has no center. The answer to where the Big Bang happened challenges every intuition we have about our origins. The story begins with Edwin Hubble, who in the late 1920s made a discovery that reshaped our understanding of reality. He observed that almost every distant galaxy is moving away from us, and the farther away a galaxy is, the faster it recedes. This relationship, known as Hubble's law, provided the first concrete evidence that the universe is expanding. It is not just that objects are moving through space, it is that space itself is being stretched. Data from projects like the Sloan Digital Sky Survey and the Hubble Space Telescope have mapped millions of galaxies, confirming this phenomenon on a massive scale. Remarkably, no matter which galaxy you stand in, the view is the same. Every other galaxy appears to be moving away from you. This creates a powerful illusion that we are at the center of the universe, but this is a property of geometry, not geography. To understand this, imagine an expanding grid or a rubber sheet with dots painted on it. As you stretch the sheet in all directions, every dot moves away from every other dot. There is no central point on the surface of the sheet from which the expansion starts. The expansion happens everywhere at once. In the cosmos, space is not a static stage where galaxies perform, space is the stage itself, and it is growing. This is often described using the raisin bread analogy. As the dough rises, the raisins move apart because the bread between them is expanding, not because the raisins are moving through the dough. This leads us to the cosmological principle, which suggests that on a large enough scale, the universe is both homogeneous and isotropic. This means that no location is unique and no direction is preferred. Whether we look north, south, east, or west, the density of galaxies and the temperature of the cosmic microwave background radiation remain incredibly uniform. This radiation, a faint glow left over from the Big Bang, shows temperature fluctuations of only 1 part in 100,000 across the entire sky. If the universe had a center or an edge, we would see gradients in this temperature or a preferred direction in the distribution of galaxies, but we see none. The idea of a centerless expansion is often illustrated with the balloon analogy. If you imagine galaxies as dots on the surface of a balloon, as you blow it up, the distance between every dot increases. A two-dimensional creature living on that surface could travel forever and never find an edge or a center. However, while useful, this analogy has its limits. Unlike a balloon, the universe does not necessarily expand into an outside space. Expansion is an internal change in the measurement of distance within space itself. The Big Bang did not happen at one point in space, it happened at every point in space simultaneously. Every point in the universe has its own observable bubble, a sphere of light that has had enough time to reach it since the beginning of time. From our perspective on Earth, we appear to be at the center of our observable bubble, but an observer in a galaxy billions of light years away would feel exactly the same way about their own position. This consistency is the cornerstone of modern cosmology. It reminds us that we are not the protagonists sitting on a central throne in the heavens, but rather a single point in an ever-growing sea of space. The illusion of being at the center is a gift of the mathematics of expansion, shared by every observer throughout the cosmos. The term Big Bang itself can be profoundly misleading. It suggests a giant fireball detonating within an empty void, flinging matter outward into a pre-existing space. If you use this image to ask where the Big Bang happened, you will never find the answer. The Big Bang was not an explosion in space, it was the rapid expansion of space itself. Understanding this change in perspective makes the question of where lose its traditional meaning. Before galaxies, atoms, or even photons existed, the universe was in a hot, dense, and nearly uniform state of energy. It wasn't a collection of things floating in space, it was space. The observable universe, which today spans about 92 billion light-years in diameter, was once compressed into an incredibly small scale. It didn't burst outward, instead, expansion began everywhere at once. Every point in that early state corresponds to every point in the universe today. Therefore, the Big Bang didn't happen at a single location, it happened within the very fabric of space. This is where general relativity comes in. Einstein's field equations describe not an explosion, but how space and time evolve in the presence of energy and momentum. The mathematical foundation of the Big Bang model requires no central point, it demands that expansion occurs equally everywhere. The most powerful evidence for this is the cosmic microwave background, or CMB. Discovered accidentally in 1965, this faint glow is not the echo of a distant explosion, but the remnant of a time when the entire universe was as hot as the surface of a star. Space expansion has stretched the wavelength of this light over billions of years, cooling it down to a near-perfect black-body spectrum just above absolute zero. We don't see this light coming from one specific direction, we see it coming from everywhere, because the event that created it happened everywhere. A common source of confusion is the question, if the universe is expanding, what is it expanding into? We are used to seeing a balloon inflate within a room, which leads us to think the universe is expanding into a larger outside. But the universe is not expanding into anything, rather, the internal measurement of distance, the metric of space, is evolving. General relativity teaches us that space-time is dynamic, it can stretch and grow without needing an external boundary. The raisins in a loaf of bread move apart not because they are traveling through the dough, but because the dough between them is rising. This leads to the question of the universe's shape. Data from the Planck and WMAP satellites suggest that the universe is remarkably flat. In a flat, infinite universe, there is no edge and no center. However, flat does not necessarily mean infinite. The universe could be finite yet unbounded, like a three-dimensional version of the surface of a sphere or a torus. If the universe were a three-torus, you could travel in a straight line and eventually return to your starting point, much like an old video game where an object leaving the right side of the screen reappears on the left. While we have yet to find definitive proof of such a repeating pattern, this possibility highlights that finite doesn't have to mean having a wall. Finally, we must distinguish between the observable universe and the entire universe. The observable universe is a sphere centered on Earth, reaching out about 46 billion light-years in every direction. This center is merely a geometric result of our line of sight. It is the limit of how far light has had time to travel to us since the beginning. Every observer in every galaxy has their own observable bubble. Beyond our horizon, the universe likely continues on, filled with galaxies and structures that we will never see due to the accelerating expansion driven by dark energy. When people ask where the Big Bang was, or what lies beyond the edge, they are often mistaking the limits of our knowledge for the limits of existence. In reality, we are simply one point in a vast, centerless, and growing sea of space. The cosmos may be infinite or finite and self-wrapping, but our perception is firmly capped by the limits of the observable universe. The beauty of this reality is that every observer sits at the center of their own observable bubble. This does not contradict a centerless universe, it simply means that the center is a geometric result of where one stands. Astronomers use redshift surveys, gravitational lensing, and data from the cosmic microwave background to stitch together a panoramic view, yet they always have a blind spot. They are limited to what light has had time to reach. Unlike a map of Earth, which uses latitude, longitude, and the poles as references, the universe has no North Star or central axis. To map this void, scientists rely on the laws of relativity. The core tool is redshift, because space is expanding, the light from distant objects is stretched toward the red end of the spectrum. This allows us to measure distances and recession speeds without needing an absolute center. Massive projects like the Sloan Digital Sky Survey map millions of galaxies in 3 dimensions based on their angular position and redshift. These maps often place Earth at the center, not because of our status in the cosmos, but because we are the origin of the observation. If a civilization existed in the Andromeda Galaxy, their map would look nearly identical to ours, only centered on themselves. To describe this centerless growth, we use what are called co-moving coordinates. In this framework, galaxies remain relatively stationary on a grid, while the grid itself expands. This is the foundation of the lambda CDM model. Within this structure, the cosmic microwave background surrounds us like a spherical shell. It is not because we are special, but because when we look back in time in any direction, we eventually hit the surface of last scattering the moment the early universe became transparent. Every observer sees their own version of this shell, centered on their own location. People often ask, if the universe is expanding, where is it expanding from? The standard analogy is the surface of a balloon. As it inflates, every point moves away from every other point, yet there is no center on the surface itself. In our 3-dimensional reality, expansion is an internal change in the metric of space, requiring no external container. For visualization, we sometimes imagine a hypersphere, a 3-dimensional surface of a 4-dimensional ball. While the radius grows over time, the center of that growth exists only in a higher dimension that we cannot access. On our level, expansion is everywhere. It is not that we are being pushed into something else, it is that the stage we stand on is growing. This expansion is now known to be accelerating, driven by the mysterious force called dark energy. This means that instead of slowing down after a hypothetical explosion, the gaps between galaxies are widening faster and faster. This further reinforces the idea that the Big Bang was not an explosion of matter into space, but the rapid unfolding of space and time themselves. Every part of the space we see today, from the edge of the horizon to the room you are sitting in, was once compressed into that hot, dense initial state. Therefore, the Big Bang happened right where you are, just as much as it happened anywhere else. Our brains evolved to understand forests and mountains, not the abstract metrics of space-time. We crave centers and boundaries, but the universe offers a centerless, growing tapestry. As time goes on, more galaxies will cross the cosmic event horizon and vanish from our sight forever. Ironically, we live in a golden age of cosmology where the remnants of the beginning are still visible. The cosmic microwave background continues to cool and will eventually fade into a whisper that even our best instruments cannot hear. But for now, the signature of the Big Bang is written in everything from the distribution of galaxies to the very hydrogen atoms that make up 75% of your body. That concludes our exploration for today. I hope these insights accompany you into a peaceful rest and inspire a wonderful day ahead. Thank you for joining us on this journey through the stars. Until next time.